one of the speakers from the more pure math side. But there will, in fact, not be any equation of the form ax equals b, because it's going to be, in fact, a purely geometric inverse problem that I'm going to talk about. In some sense, my talk is going to be basically the orthogonal complement of the talk that Yiran Wang was giving yesterday about inverse problems for nonlinear wave equations. And so he explained, and I will recall that later in the talk, how you can use the nonlinear interactions of waves to generate artificial point sources somewhere else, and then you get singularities propagating out of those. And so then you just measure the location of singularities, and then he just used as a black box that somehow from knowing this, the location of singularities sort of coming out of some point source interaction, you can, in fact, recover information about the material or the interface and so on, where that interaction took place. And so I'm going to focus on this geometric part, namely, suppose you have some point sources generated in whichever way you want to think about. For the purpose of this talk, let's not go to elasticity, but just the acoustic wave equation. But some of the speed of sound could depend on the direction in which signals are propagating. And in fact, the material could also vary in time. Okay, so now you consider some point P inside your physical body. So some of the horizontal plane is the physical body, and then time goes upwards. And you have a signal that emanates from a point P inside of your body X at a certain time T sub P. Okay, so now from this point here at that time, if you wait 1 second, the signal will have propagated a little bit in all directions. And so if at some point the signal will hit the boundary of the physical body that you are considering, and so, for instance, you have seismometers on the surface of the Earth, and so these measure the time at which the signal arrives at the surface and the location, of course, where the signal arrived at. And so now the mathematical toy model that I'm going to consider is, I'm going to state it more precisely soon, that you have a whole bunch of these points, so a whole number of points, and from all these points at various times, these signals get emitted, and so you measure for each of these signals their time and location on the surface of the body. And what you want to do is you want to recover the inner structure of X, or more precisely, really, the inner structure of the set of sources where the signals came from, by making exactly these measurements of just time and location of when these signals arrive at the surface. And to make it sort of more interesting and more realistic, well, you don't have seismometers on every point on the Earth, so suppose you only record measurements on part of the surface, so say only sort of on a little circular arc here. So we want to consider this sort of more narrow situation. And then, so one immediate issue that will show you that this is sort of, that the reconstruction that you're going to do is going to be somewhat abstract, is that the best thing you can recover is, well, I'm going to tell you in a second, but is basically the direction. So you can recover the set of sources and sort of the direction at every point in which light or waves will propagate. What you cannot do is to somehow determine some label of the time at which the signal was emitted sort of in the interior of the Earth. Right? You could imagine, for instance, a situation where the speed of sound is, I don't know, 1 kilometer per second, and then some signal gets emitted from somewhere in the interior of the Earth, and then it takes, okay, I don't know, an hour to reach the surface, and then you record it at some point. But you could also think that the speed of sound is actually just half of that and was emitted somehow twice as, so half that, but it was emitted 2 hours earlier, so it will take 2 hours for the signal to reach you, but it will give you the same measurements on the surface. So somehow there's no intrinsic time attached to these measurements that you can make that tells you how long it took for the signal to reach you, okay? So you do know when you measured the signal, but you don't know how long it took for the signal to arrive at your location. So this is somehow already a caveat that you will not be able to determine this. So you don't know timestamps of signals emanating, but you can try to recover as much else as possible from these measurements. Okay, so before I proceed, so I said I'm a pure mathematician, so the practical aspects of this are, at this point, not very clear because, well, you will have a whole lot of point sources, And in fact, you need a continuum of point sources for what I'm going to talk about. So in reality, you would only have some finite number of sources, like a finite number of earthquakes or a finite number of explosions or something that you can set off. And so then you will only have some finite number of measurements, and you somehow want to reconstruct the inner structure of your body as precisely as possible. So that sort of you only have a discrete set of measurements rather than a continuous set. And this would play into what Matti Lassas was talking about on Wednesday about manifold learning. Phrase this more geometrically, which in particular takes care of sort of this part that you cannot determine sort of timestamps, but you have to proceed more abstractly in some sense. And so a very nice geometric framework for doing these kinds of things is Lorentzian geometry, which comes originally from general relativity. But if you don't like light rays or gravitational waves and so on, which you should, then just think of acoustic waves, for instance. Okay, so the model, the simplest model, let's just stay in a number of dimensions that I can draw. You have 2 spatial dimensions and 1 time dimension. Then the simplest Lorentzian geometry is that of Minkowski space. And so it's the following simple manifold M. You just have a time direction and 2 spatial directions. And you equip it with this metric, which is not a positive definite metric, but has this 1 minus sign. So the nice feature about this kind of geometry is that there are these special vectors called null or light-like or sound-like, if you like, vectors. Namely, these are those tangent vectors whose squared length is equal to 0. So here's a very simple example. Namely, you take the vector that takes you 1 step forward in time and 1 step off in space. And so this going 1 step in space after 1 step of time means the speed of propagation is 1, sort of in my unitless notation. And so in this way, these Lorentzian metrics directly encode the propagation speed of waves. However, they do not, oh, okay, let me just keep it at that so far. So here's a picture of the light cone. So these are all the vectors, so it's a cone of vectors, which have this null property. And so I drew the one that goes 1 forward in time and 1 in the x1 direction, let's say. Okay? And so future null vectors, the collection of those is exactly the collection of vectors along which signals or waves would propagate. Of course, there's also the past version of this, which is the directions from which signals or waves reach me. But if you're about to set off explosives, that usually happens towards the future, not the past. Okay, so the more general picture then is that of a space-time. So it puts space and time together into one single object, where somehow there is no preferred time notion anymore. And so now you have n spatial dimensions, 1 time dimension as usual. Then you have a metric where the time dimension gets this minus sign and the spatial directions have the plus signs. So the simplest example is sort of that I have been implicitly talking about before. And we just have some time direction, some physical body x. And then you have a time varying, say, travel time metric on your physical body x. And so you write down this space-time metric g like this. And so again, the point is that this metric g encodes the directions along which light or signals will propagate. And you go 1 step in time, and then however far you have to go, what measures 1 step, 1 meter, say, in space. And so more generally, these Lorentzian manifolds are meant to look locally like, well, you have a time direction and some isotropic body sort of on very small scale, so they're smooth kinds of objects. So mathematically speaking, the tangent space at every point Q of the manifold looks like this model form, namely this Minkowski space that I had on the previous slide. Okay, so then you can also geometrically generalize this notion of these light rays or rays along which signals will propagate, and these are called null geodesics, at least in the relativity literature. And so you take your favorite null vector, so you're at a point Q in your space-time, meaning you're at a certain time and at a certain location in your physical body, and you decide on a direction in which you want to send a signal, so that's V, and then you just look at, well, where does the signal now travel through your body, and it's going to follow one of these null geodesics. And so the future light cone is just the collection of all these outgoing null geodesics. So here is sort of an artist's impression. You have this point Q, and the material is anisotropic, so somehow it doesn't look like a nice cone anymore, but it somehow has these slight wiggles. Yeah.
Is there any constraint on how the metric can change from point to point?
So I'm going to give you the assumptions for the theorem in a second. Yes. but it's fairly general, so it can be basically any smooth Lorentzian metric with some extra properties. Okay. Okay, so here's the inverse problem that we study. So this is all joint work with Gunther Ullmann. This is the inverse problem that we study in this model case. So again, for the sake of imaginability, let's go to 1 plus 2 dimensions. So again, you have one time direction, 2 spatial dimensions. And let's say the Lorentzian manifold we look at, well, it exists for all time, and it's just all sets of points in a disk of radius 1. It's very simple. So the physical body you could think is exactly that disk. And let's just suppose the metric has this nice form. Okay, so some time-varying acoustic metric in your body. So now you have the set of sources, S. So I depicted it here. And from each point in the set of sources, each point Q, you look at the outgoing light cone from this. So it's drawn here. And then at some point, it reaches the surface of your body. And in this case, I just drew it so that in the set U, this blue set, you actually make measurements on the entire surface of the body X for some limited amount of time. So somehow you start measuring here, and then you turn off your detector right there because you didn't get paid enough. Well, I don't know. So you make these observations in the set U, and what you measure, the set of data, is really just this collection of measurements. You only collect when and where did these signals reach you from any one of these sources. And the theorem then in this special case says that just the collection of these measurements here determines the topological differentiable and conformal structure of the set of sources. So what do I mean by this? Well, first of all, the only thing that I actually know about my body is the part of the boundary that I live on. I don't know whether the body somehow has some holes inside or what's going on. Okay, so I really only am given these data, and I know my laboratory U, where I measure things very well. And what I claim is that from just having this list of measurements, what I can do is I can recover, well, the set of sources. First of all, as a set, well, that's pretty obvious. I just have the collection of all these measurements, and each measurement corresponds to a certain source. But I can also determine the topological structure. So I can recover S as a topological space, which means that I can determine when 2 point sources are close just by looking at the corresponding measurements. That's not too surprising because you would think that, well, if the 2 points are close, the corresponding measurements will happen roughly at the same time, roughly at the same location. There are some sort of caveats which make this a little more tricky than you think. The differentiable structure of S, that means that you can, just from looking at the measurements, write down sort of a local coordinate system on this set S. So you can somehow assign some abstract coordinates to the points in your mystery set S. And again, these coordinates will, so it's sort of a stronger notion than the topological structure because, well, you actually get to assign. Yes?
What you're saying is that if I measure around the whole disk, then there's a unique reconstruction? Is this what you're saying? So the collection that you're talking about is the measurements, you assume continuous measurement everywhere?
Yes, so the set on which I measure is going to be, later it's going to be more general. So it's an open set. So you imagine that you have some of your laboratory. At every point of the laboratory for some interval of time, you record things. And then as long as, of course, for every source here, a signal reaches you in your laboratory within that time span, then, yeah, once you just have this collection.
I can find counterexamples. I can find 2 different sets of sources which would produce identical measurements?
Yes, I'm actually going to give you some examples. Yeah. So not quite for this, but yeah, almost. Okay, so that's the differentiable structure. You can assign coordinates, and you actually know also the dimension of the set S if you're interested in this. And the conformal structure, finally, that's the best you can hope for. It means mathematically the metric up to rescalings. And so if you go back here, then you see that for a vector being null, if you rescale the metric, this condition is still going to be satisfied. Null times a constant is still null. And so that means that you can at best recover the metric up to this rescaling, but you can rescale at every point differently. So some of what this rescaling does is it gives you a different time scale at each point. So some of what you cannot recover is what I sort of indicated earlier, some timestamp of when the signal was emitted. That you cannot do, but you're geometrically not able to because all so your measurements are independent of the special conformal choice of your metric. Okay, so that's some of the theorem in this model case. In this model case, it's very simple to do because you can just, well, you take your favorite point here, you can just explicitly calculate so if the metric was actually dx squared here, you can just explicitly calculate what the boundary light observation sets. So these green guys here look like. And then you see, well, it's a continuous, in fact, a diffeomorphism from the set of sources to the set of data. But, okay, so here, the more general theorem is, well, more interesting than that. Okay, so one thing that I haven't drawn here yet, which, however, is you can also easily allow for, is that suppose you have some signal happening at some point in your body, the wave propagates and reaches some part of the boundary where you actually didn't have a measuring station, but then it gets reflected off of there, and it travels to some other point where you do record things. And so, well, how do things reflect? Just according to Snell's law, so here's the picture in space-time, something propagating forward in time and reaching the boundary, and then it gets reflected here. Incoming equals outgoing angle. And so I call these continuations of null geodesics or paths of signals broken null geodesics. And so geometrically, it's very nice to assume that the physical body is convex, which means, sort of intuitively speaking, that all these null geodesics always hit the boundary of your body transversely. If that weren't the case, if somehow your body was sort of shaped convexly, then something comes in and then it hits the sort of, so if it barely misses it, it just goes in a straight line, but if it doesn't barely miss it, then it somehow gets reflected off quite drastically, and so this is geometrically unpleasant. So to make life simple, let's just assume this doesn't happen. And so here's a geometric reformulation of this in terms of the extrinsic curvature of the boundary. Okay, so let me not get into the details of this. So as I said, we now define these light cones here, not just by looking at the geodesics, but in fact looking at the broken null geodesics. Okay? Oops. Okay, so here's then the more precise statement that hopefully answers then the question earlier. So the setup is that you have this Lorentzian manifold Mg, well, at least two-dimensional. Physically, you would be interested in 4 dimensions, with this convexity condition on the boundary. Then you have some, you want to assume that there is some sort of time function on this manifold. The properness just means that, well, the set of points in your spacetime which get assigned t equals 0, some compact set. So that's very reasonable because any physical system is most likely bounded and closed. So you have a set of sources that is a subset of the interior of the Lorentzian manifold. So in other words, every point in here has a time label and some spatial label, intuitively speaking. And you make observations in some open set on the, of the boundary. And the assumptions under which you want to recover from these measurements the interior structure of the set S is, well, first of all, you want to make sure that any 2 sources generate different measurements. That's an obvious assumption. If 2 sources somehow generate the same measurement, you wouldn't be able to distinguish the 2. And there's some geometric thing. You don't want caustics to happen sort of from a point source at the boundary. So that's a technical condition. And so then the theorem that we proved last year states that if you know this smooth manifold U here, so you know exactly what your laboratory looks like, and you're just given this unlabeled collection of measurements. So you just, for each signal, you just sort of have one folder. And so you have a whole bunch of these folders, which is the collection of these light observation sets. Then from these, you can recover the set S and the metric tensor there exactly in the sense. Namely, you can recover the topological structure, determining what points are nearby. You can write down local coordinates if you like, and you can recover, most interestingly, the conformal class, which means you can determine sort of the anisotropic sound, well, yeah, anisotropic sound speed in a certain sense. Okay. Any questions about this? Sorry? Well, I mean, you have very serious trapping in the sense of if you just have a finite body like the Earth, then stuff can sort of go away. But it's not trapped in time. So, you know, every signal propagates forward in time. So in that sense, there's no trapping.
I was thinking spatially trapping with it.
Well, the time always goes forward. So eventually, if you just measure, say, for a finite amount of time, eventually all signals will go past you. Yes. So in fact, the time-like assumption here makes that happen because every signal has to somehow cross t equals constant surfaces transversely. Mm-hmm.
I'm trouble understanding the equivalence class. So G restricted to S. So it's an equivalence class.
Oh, right.
Of metrics up to rescaling.
Yes. So it's this one here. So in the Minkowski example, let's go back to this one. So this metric here. So this vector here, go one in time and one in space, that's always a null vector, even if you replace this metric by 7 times this metric here, right? Because the null vector is still going to remain null. But if you remain at a fixed point, say x equals 0, and then wait until the t coordinate reaches value 1, you cannot, so for this metric, 1 second would pass, but for the 7 times this metric, 7 seconds or a square root or something like that would pass. So somehow you cannot, you don't have a time scale. But what you do know is if you go one step in whichever units you say that in the time direction, then you know exactly how far in space you have to go to continue along one of these null curves.
You lose the units of time.
Yes, yeah. But that's intrinsic in the problem setup because the things that you actually measure don't carry units of time with them. Yeah.
Can the sources be arbitrarily close to the surface or the boundary of the manifold?
Yes, yes, it can be.
Do you know what the minimal condition is if you reintroduce it to recover the times?
That's a very good question. I'm going to give you some references later about something very closely related, yes. Okay, so that's the theorem. So let me just give you some more examples. So basically the example that probably, hopefully all of you had in mind was basically this simple product example. You just have a time direction and then you have some physical body that's actually not changing in time at all. And so that's sort of the simplest situation. And so then the strict null convexity assumption is in fact nothing else but the convexity of the physical body itself. So it's a very natural thing. Here are some more examples. So now here the manifold, think again of the Earth now being just, well, I'm a flat Earth proponent, so here it's just this. And then time goes on, and somehow as time goes on, the metric on the Earth varies a little bit. And here's another example where somehow the boundary of your body is somehow this U-shaped thing. And so you have a point source here, then signals propagate, get reflected here at the boundary, and your detector is here. So in fact, one signal produces sort of two different traces of the signal coming here. So that's a situation that you have to deal with. Okay. So these are the examples. Here are some counter examples along the lines of the second question I had earlier. So here's the simplest counter example for being able to recover this set of sources. So consider this very symmetric situation where your body is just a one-dimensional rod, so somehow going from left to right, and then time, as usual, goes upwards. Suppose you somehow ping the rod in the middle, and then the waves will propagate to the outside, then it will come back and refocus exactly on the same point, and then it will, the signal will sort of keep propagating. So that's what's happening here. You ping it, it propagates, gets reflected, goes through the same point again at a later time, and then eventually somehow you waited 2 seconds instead of just 1, and you measure, oh, the signal somehow arrived here at time 2 seconds at this location. Okay, but you can see clearly from this picture that whether you ping it now, wait for one reflection, and then measure it, or whether you measure it directly somewhat from the later time, gives you the same measurement. So you cannot distinguish the 2 point sources here. In fact, these 2 sets look exactly the same from the point of view of measuring only at this point in time. Okay, so that shows you that indeed you can have a situation where measurements look the same even though the point sources were different. I mean, you were asking about you only make a finite set of measurements, and I'm sure in this case you can engineer similar things, yeah. Here is sort of a slightly more degenerate, or, well, slightly more nasty situation. Again, you have this rod, but now it's contracting ever so slightly after you do the first ping. So what happens is that if you do this first ping here, then the signals propagate, but somehow it was contracting initially, so somehow it doesn't refocus quite at the same point, but very nearly so. And so somehow this point here and this point here generate extremely similar measurements. So any reasonable person would suspect that the corresponding sources have to be extremely close, but you see in this picture that's not the case. And so that's yeah, so that's why we assume that indeed for elements of the closure of the set of sources, the observations are different. Okay, so that's as far as counterexamples go. And so let me put this into some context. So this is some of the boundary value problem version of a paper that was already mentioned yesterday, and I suppose 2 days ago, by Kuriles, Lassas, and Ullmann from a few years ago. And they study a closely related problem where you now have a boundary-less manifold. Imagine our universe, so space plus time, and well, it's a geometric assumption, in at least 3 dimensions. Again, physical dimension would be 3 plus 1 equals 4. And now you are an experimentalist, mu, and so you live on a time-like curve. So basically, imagine you're stuck in your laboratory. Well, that may be your grad student, but anyway. And so U is the laboratory, and so the grad student stays in the lab from 6 a.m. to 10 p.m. and makes measurements here and measures when signals emitted from sources somewhere else in the universe hit the lab, where exactly they hit them and at what time they hit them. Okay, and so this, the set of sources is located such that, in fact, signals do reach your graduate student. Okay, so your emails somehow are out here. They don't reach your student. Okay, so then this, the theorem in this case is, has the same kind of statement, namely, if you know your lab very well and you measure these observation sets, then you can determine the structure of the set of sources together with this conformal class of the metric that I explained earlier uniquely. And so sort of some technical comments about this are that you can get around these conjugate point or caustics because you can always sort of move just an epsilon away from a caustic and you're off of it. You can also reconstruct the metric itself, so the time scale as well. If you make some extra assumptions, for instance, something in general relativity that the metric is Ricci flat, that would work. And also, this only uses the earliest light observation set. So somehow there's no reflection happening at any surface. And so that's somehow geometrically simpler in that sense. Okay. And, but otherwise, it's very similar in spirit. Okay. And so the reason, or the way that this fits into the talk by Yiran Wang is the following. So he talked about these inverse problems for nonlinear wave equations. And so the setup is the following, that you, well, you have some sources f that you can play around with yourself. You solve this, say, box u equals u to the 4th plus f nonlinear wave equation. And then if you know, so if you know the map that takes a source that somehow generates a nonlinear wave, and you know the map that assigns to this source the solution of the wave equation in your laboratory, then from this you can recover the space-time surrounding your laboratory together with the metric, in fact, together with the time scale in this particular example, because the nonlinearity sort of has a very simple structure. And so what's great about this is that some of these, which was the great insight of this paper, is that if you study nonlinear inverse problems, you can in fact have much better theorems, can recover more complicated geometries than if you only look at linear inverse problems. So that's some of the take-home message from yesterday's talk. And so, yeah, please.
When you say determines, does it bottom out into an actual algorithm? Even if it's intractable, is there?
Yes, it's a reconstruction. It's not just uniqueness, but yeah, you can recover it completely. So I'm going to show you in the in my case that how this works. Okay, so let me just. How much time do I actually exactly have? 18. Okay, very good. Okay, so the way that these two fit together, let me just remind you, in case you missed yesterday's talk. So let's go down one dimension just so I can draw a picture in one slide. So you look at this equation, box u equals u cubed plus f. The question arose yesterday, if you're down one dimension, you need one fewer wave to actually generate these point sources. So that's why I go to u cubed here. And so the idea is that you use the nonlinearity to generate new point sources outside of your laboratory. So the idea was that you take as your sources a linear combination with your favorite small coefficients epsilon I of certain model sources fi, which are designed to actually produce nonlinear waves which propagate sort of like a plane wave, like a wave front. Okay, so you take a normal distribution. Here is a silly example. So, well, sort of at t equals x1, sort of this is this outgoing kind of sheet, you have the singularity propagating. Okay. And so then the solution, if you just, well, forget about the nonlinearity for starters, then the solution is going to be the linear superposition of the solutions ui of the linear wave equation. Now you plug that back into the equation up here, you get the u cubed, you use the binomial theorem, and you get, if you solve that away, this extra cubic term here from the interaction of these three waves that were produced from these sources fi. Okay, and so then what you're interested in is exactly this coefficient here, so the coefficient of this cubic interaction. And so here's the picture. Okay, so you have, again, this cubic interaction. You had these three waves propagating, so one comes from here, from here, from here, and they interact in a single point that I'll label Q, and from this point, the wave generated by this, so the wave generated by this will be singular, essentially exactly on the outgoing light cone from that point. So that's what Jeroen talked about yesterday in great detail. Okay, so here's sort of the mathematical statement. There's one point where all these waves are singular, and then at the interaction point, they generate a new singularity propagating in all directions. Okay, and so then that's how this connects to the geometric inverse problem, because if you know the singularities of this generated point source, well, these singularities are exactly these light observations that you just measure, well, where is my solution singular? And that tells you a light observation set. But the point where the signal came from is away from your laboratory. You don't have access to this. So somehow it's really some sort of abstract set of measurements that you get this way. And what you want to recover is, well, what does the outside of my laboratory look like if I only have this collection of measurements within my lab? Okay. And so then you can, of course, ask similar questions for the boundary value problem. And so that's, it should be work in progress with Gunther. And here's, again, the same kind of model in 2+1 dimensions so that I can draw the picture. You look at this, the same, say, nonlinear wave equation, Bach equals u cubed. And now what you do is, instead of somehow planting sources, you're allowed to impose Dirichlet data on some open set of the boundary. So somehow you have access to your physical body at some region of space and for some limited amount of time. And so then you can somehow set up boundary sources. Then they will propagate into the interior of the body. There will be some interaction happening. And at some later point, your colleague in Italy or something measures the waves reaching your colleague in the sense of measuring the Neumann data of the wave. And what you want to do is, from knowing the map that takes boundary data in the red picture here to Neumann data over here, you want to recover as much as you geometrically or analytically can from this source to solution map. And so there's a special case that would be the easiest to study at first, which is that you, in fact, make measurements and boundary conditions on the same set, because then, well, you can work locally, right? You set off some sources, then there's some interaction happening right underneath the surface of your object, and there's some nonlinear interaction happening here that reaches back to you after a split second, and so you can sort of try to reconstruct things locally. Okay, so this is a natural, the natural analytic counterpart to the geometric theorem that I'm talking about. Okay, so just a technical comment that this convexity assumption makes then the analysis also more amenable, because if you have concave boundaries, then singularities can propagate in all kinds of complicated ways, which one better avoids. Okay, so let me try to explain to you some of the ideas of the proof. So let me recall the setup here. So you have this Lorentzian manifold, some time function set of sources, and you make observations. And then you want to recover from just the set of observations, the set of sources, and sort of the geometric structure of that. And okay, so what's the basic, I mean, the first step to set this up? Well, you know what structures you should get at in the end. So somehow what you want to do is, okay, you have the set of sources, and imagine you already knew exactly what it looked like. So for instance, you could exactly, you know the topology, for instance, on the set S, so you know what 2 points are, when 2 points are close. Then you just declare, well, I'm going to declare 2 observations to be close if the original points were themselves close. Or I'm going to assign some coordinates to a measurement by just assigning those coordinates which I assign to the source point. Okay, so I already have some reference structure on my set of measurements that I want to recover without knowing the original set or the geometric structure. So somehow just then using the set S, so script S of my observations, I want to be able to recover these reference structures. Okay, so let me skip this difficulty here. And okay, so what is clear from the way I set this up is that, well, the set of measurements is somehow a very abstract object, right? It's just a collection of sets. And so somehow a collection of sets with, at first, no other structure. And so if you want to somehow reconstruct the topology of this, or what smooth functions are, or the conformal structure, it's just going to be some structure on this abstract set. So somehow it doesn't actually tell you, well, there's a rock that looks like this, and so on and so forth, where the sources came from. So somehow this is, yeah, just recovering as an abstract conformal Lorentzian manifold. And then if you actually wanted to have some more, like a nicer picture, then you would go to Matti and ask him to reconstruct a Lorentzian manifold out of this abstract structure. Okay, so and here's an example in the middle that shows you that this is sort of a little delicate. So if you imagine you have some point source at some point, so the reading is like this. So that means, so imagine at every vertical line you just have a detector that's just standing there, and at this point in time it detected a signal. Okay, so same here. So there's a signal coming in here, and there's another signal that looks like this. So somehow up here it looks like these signals are very close, but down here there's this extra thing. What could have happened is that you had a signal that emanated, then it got reflected, and then you measured it. That's the first one on the left. The second one is, well, you had a signal that was emanating from a slightly later point, and you happened to detect the first intersection with your detectors, and then it got reflected off, and you measured it again. So you measure this, you measured sort of the event Q2 twice here. But still, these two events are very close, even though this one is completely lacking some first measurement here. So that somehow tells you that you have to be a little bit careful in how to compare two sets to be close. Okay, so then you look at sort of later and later sources. So this one also you record two interactions with the boundary. And so for this one, you miss the second one. But somehow these should all be very close by events. So you have to be a little bit careful. And so here's not too careful, because here's the easy way how you can do this. So how do you declare two events to be close by? Well, you just look at your at the set where you make your detections, and you take your favorite open set on the surface of the Earth and your favorite open interval of times on which you measure, and then just declare two measurements to be close, meaning they both lie in the same open set A sub O, O being some of this open region of space-time, if measurements, so if in this region of space and time you actually recorded a measurement, okay? So this I declare to be an open set, and you can do sort of the complementary thing, namely you don't want to see a reading of an event in your favorite compact set. Then you also define this to be open. So here's a picture. So here's an open set, and this measurement here lies in the set A sub O, because you say, well, this measurement, so this point source here actually generated a measurement that I recorded within my small pink region of space and time. And it also lies in the set B sub K because it missed, so it did not leave a trace in this compact set down here. Okay, and then you can show under the assumptions of the theorem that in fact the topology generated by these sets, so you take intersections and unions, so finite intersections and arbitrary unions, the topology is equal to the reference topology on S coming from the set of sources. So in other words, by just looking at the set of measurements that you have, you can recover what it means for two things to be close by. Okay, so here's the smooth structure. This is very similar in spirit to the idea of these earliest observation sets. So suppose now you had some event coming from somewhere, and you detected it at a certain time. And so mu, that's you, or that's your seismometer, detecting the event at a certain time, mu of s. So somehow s is the time at which you measured it. And then you can just say, well, if I have a slightly different event, I'm just going to record the time when my same seismometer mu detects this event. Okay? So that's a very natural construction, and so you make this sort of more precise. So you take a smooth curve that's transversal to the measurement set, and has exactly one intersection with the measurement set, then nearby observation sets will also only have one intersection with your seismometer. And so you just declare the time at which an event hits that seismometer to be a local coordinate. Okay? So for each seismometer, you get one coordinate. So if you have a whole lot of these seismometers, you get a whole lot of coordinates. It turns out that you can prove that these coordinates are smooth in a subset that you can also specify from just knowing the sources. And so some of the smoothness exactly uses the assumption that you have no conjugate points, and also uses the assumption that the boundary has this convexity. Again, because, well, if you didn't have convexity, then sort of two nearby signal paths could be quite vastly different. So they would give you Lipschitz coordinates, but nothing more smooth. Okay, so this gives you some local coordinates, and then you prove that, in fact, if you take n+1, so remember n+1 is the dimension of your spacetime, if you take n+1 suitably chosen seismometers, for which you record the time at which an event hits you, that gives you, so this is the mathematical formulation, the differentials are linearly independent. That just says that the corresponding observation times x mu naught until x mu n give you local coordinates on the set of sources. Okay? And so then you can recover the smooth structure, meaning you can declare when a function is smooth, namely it's smooth if and only if on every open set it's a smooth function of these local coordinates. Okay, so that's a mathematician at work here. And then you prove that, in fact, this collection of smooth functions is exactly the translation of smooth functions from your set of sources to smooth functions on the set of measurements. Okay, and so then once you know what smooth functions are, you can also talk about what local coordinate systems are. Okay? So, and then the last step is that you can recover the conformal structure, and that's, so what does that mean? So now we have sort of this abstract, okay, we have the set of measurements, and now you visualize it as, well, that's the set of sources. I already know when 2 points are close by. I have some local coordinates on the set of sources. What I want to determine last is this conformal structure, which tells me, suppose I have 1 point in my set of sources, and then I want to determine basically the path along which a signal would propagate. So somehow I want to recover a null geodesic within my set of sources. And so how do you do that? Well, the intuitive picture is actually very simple. So suppose you have some source that generates some light cone. It hits you at your seismometer eventually. And so if you just take, okay, so you look at the path from your source to the point where it hit your seismometer. And then if you take any other point along this very path, then a signal emanating from that point will also hit your seismometer at the exact same point in time. And not only that, but also the light cone will in fact have the same tangent space at the seismometer. Okay, so turning your head around is if L here, so this green thing, is sort of local linearization of the region where the signal hit you. Okay, so again, it's sort of parameterized by location and where, at what point in time it hit you. And so then you can uniquely reconstruct the direction along which the signal was actually propagating just prior to hitting the surface. And so that's this red arrow here, the V. And so then you just trace it backwards. And if you follow this direction backwards, eventually you will hit your source point Q, where the signal emanated from. And what I just explained is that on every point along this backwards path, the signal emanated from there will hit you at the exact same point P, and sort of with the same linearization here. Okay, so the geodesic, starting at your observation point, going backwards, sort of inwards into your body, contains the source point. And so that tells you that null geodesic segments within your set of sources can be detected by just noting that if you look at the future light cone emanating from such a point, it will contain the point P on the boundary and will have the same tangent space. Okay, so you can detect whether a collection of sources lies on a null geodesic by just looking at the measurements that you do and checking whether the tangent spaces are the same at the same point. Okay, and so then you vary the point at which you do this construction, and you can recover an open subset of the light cone at every point. And okay, so what is the light cone? Well, it's just a sort of quadratic variety, right? It's just sort of tau squared minus xi squared equals 0. That's sort of the model. And so if you know an open subset of this, you know the entire thing. right? You only have to find whatever n plus 1 over 2 parameters. Okay, and so then, of course, so again, what this tells you is that for every point in your set of sources, you now know in which direction signals will propagate. Okay, and so that basically finishes the proof. So there are some very natural continuations of this which you can look at. For instance, you could try to recover not just one, but n Lorentzian metrics from knowing the observation sets of all n combined. So this sounds a little silly, but for instance, isotropic elasticity would give you some sort of natural example of this, where you have two sound speeds, namely one from p and one from s waves. And so you can try to recover both p and s wave speeds sort of in this geometric manner. Another natural problem would be to consider not boundary value problems, but initial value problems, where you somehow do something at some initial instant in time, and then you see how the wave propagates, and then you measure, for instance, the solution in some open set in your lab, or you measure the solution somewhere at the boundary of your body, and so on. And then you ask, how much of the body can you actually determine? And this is also particularly natural for the Einstein equation, which was mentioned several times before.